Okay, so welcome to this session at IWOTA 2021. So it's a pleasure to introduce Professor McCullough, who will discuss bianalytic mappings between three spectrahedra. So please, Scott.
Okay, yeah, so I'd like to thank Daniel and all the organizers for the invitation and putting together the conference under the sort of trying circumstances. So, yeah, so let me mention what got left out in my abstract was some of the co-authors. So there's the Merrick, Munir Benjama, who's an undergraduate at the University of Florida, Eric Ebert, Bill Helton, Igor Klepp, Nicole Tuvilla, and Yuri Volchik. I think I've got everybody. So let me get started then. So let's see, so we'll have a fix throughout the talk. G will be a positive integer. And then here we'll use, so D by E for D by E matrices, complex entries. And given a tuple then, a G tuple of such matrices, we'll let lambda E denote this linear matrix polynomial. So we're thinking of xj as just some variables. And then we'll want to evaluate that at tuples of matrices as well, of varying sizes. So say if we have a G tuple of n by n matrices, we'll evaluate our matrix polynomial, our linear matrix polynomial lambda at the tuple x just using the tensor product. And then like so, and so you end up with a matrix. You could think of it as a D by E matrix with n by n entries, or maybe you want to think of it as an n by n matrix with D by E entries, or maybe matrices of size n D by n E, it doesn't really matter. And I tend to think of the tensor product as being just algebraic, but if you want, you can interpret it as this Kronecker product. So here I wrote it with picked a couple of simple examples, E and X. And you could think of it as you just take each element of E and multiply by X and get a block matrix, or you could do it, of course, the other way around. And then up to unitary equivalence, it's all the same. And you could even, I suppose, think of this as X tensor E if you wanted. But, and again, just the sim symbols for unitary equivalence. Yeah, then when A is square, say R by R, we can form what people call a linear pencil. Well, maybe monic linear pencil. It's not really linear, it's affine linear. The monic part would be, we have the identity here, and then we have our linear polynomial lambda AX, and then I'll just leave this as it is, just sort of a formal adjoint variable here. So we take the polynomial lambda A X and take some sort of formal adjoint. And then the way to interpret that is what happens when, maybe I should write here, when we evaluate the monic linear pencil L, right? So we're going to evaluate the R by R identity by tensoring with the identity size n for, say, X, a tuple of size n. Oops. And then the lambda AX star is just what you think, right? It's just, you just take the adjoint of AJ tensor XJ star, and that's just going to give you the adjoint to the AJs, tensor the adjoints of the XJs. Okay, so that's maybe just a simple ad hoc way to interpret that adjoint, the star. And so here's a simple example, if you haven't thought about this too much recently. We take A1 and A2 here as pictured, and then L sub AX is a polynomial where it's got the identity, and then it's X1 times A1, and then X2 times A2, and then we'll have X1 star, some adjoint variable, times A1 star, and X2 star times this adjoint variable X2 star times matrix A2. So there's an example of a monic linear pencil. And then this expression, LAX positive, so we use this positive semi-definite, is just that formal expression is what I think of as a linear matrix inequality. And then, of course, we're interested in actually instances where this inequality holds. It's the place maybe to start is where you take your tuple X just to be a tuple of 1-by-1 matrices. So that's just the tuple, the G tuple of complex numbers. And we'll look at those X for which this monic linear pencil is positive. Those X for which LAX is actually positive definite. So that's the scalar, you would say, scalar level solution set, feasible set of this linear matrix inequality. And it's what is known as a spectrahedron. And then some reasons you might care about spectrahedron, spectrahedra is they appear, the basic objects in convex optimization, semi-definite programming. They appear in real algebraic geometry, say in particular in determinantal representations, and they're sort of everywhere in engineering systems and control. Sort of problems that you can reduce to a linear matrix inequality, or you can sort of think of them as solved, right? Because there's a good numerical methods for them. And so here's an example. So why the real algebraic geometer might care. So I'm cheating here a bit because I've taken the A's here to be self-adjoint. So, and I've taken the variables to be real. So I'm special, it's a slightly different setting, but it makes a really great picture, thanks to Igor. So you can look at this monic linear pencil LXY and look at its, where it's positive, that will give you the interior of this elliptic curve. For instance, the solid red line is then dead equals 0. And then what we'll be interested in is it's not what happens at the scalar level, but sort of what happens across all levels. So what I mean by a level is, say, a dimension. So I'm going to call it level n. That's where we're going to look at G tuples of n by n matrices. And then substitute, look where that's positive definite. So we'll call that P for positivity, perhaps, positivity domain of this determined by this tuple A at level n. And those you could think of as relaxations, if you want, of spectrahedra. This is some sort of relaxation, maybe a free relaxation. Free spectrahedron is what you get by considering all the levels simultaneously. So the sequence or graded set. And then it's trivial to see that at least level-wise, these sets are convex. They're defined by linear equations. And in fact, there's some convexity that transcends across the various levels as well that we won't really need to discuss, but it has a property known as matrix convexity as well. And then just a word of caveat, I will be sloppy about various hypotheses. But I'm assuming everything is, the A's are linearly independent. Whenever I have a tuple A, it's going to be independent. And then all these spectrahedra, free spectrahedra, I'm going to assume are bounded. Okay, and then a couple of examples. We had already looked here at what you might call the column ball, where we take this pair A1 and A2, and we get that gives us this linear pencil. And if you look at the spectrahedron, so that's this set here, what happens at level 1? So we're looking at two tuples of complex numbers, and it's simple to check. It's just a sure complement argument that that's just the unit ball in C2. If you look at higher levels, what you get is what people might refer to as the column ball. That's this condition right here. That x1 star x1 times plus x2 star x2 is less than the identity, right? It's just really this condition that x1, x2, this column matrix you get with block entries, of course, has norm less than 1. So a slight variation is, I've just made this name up, what the heck, twisted ball. By taking B1 equal to A1, but then B2, just put the 1 here in the 2,3 entry instead of the 1,2 entry. It gives you this monoclinear pencil. And again, if you just look at at level 1, again, it's not hard to see that you just get the unit ball in C2. But at the higher levels, you have this condition here, right? So you're really asking maybe that X1, X2 star is in the column ball. So you get some sort of twisting there. Another example, simple example worth looking at is the free, what I call the free polydisc, say in G variables. You're just looking at G tuples where of matrices of some size. So I've dropped even putting the sizes here. It's understood we're grading over all n. So you're just looking at tuples, G tuples of matrices of the same size, of course, that each have norm less than 1. And then if you want to actually write that using a monoclinear pencil, well, here it is. You take this 4x4 gadget, and you get this pencil, and the upper left corner is telling you that X1's a contraction. The bottom right corner tells you, well, that X2 should be a contraction. If you're going to ask that this be positive definite, when you plug in matrices X1 and X2. And then so a special case then is of spectrahedra, or what is spectral balls. So if you're given the tuple E, so not necessarily square now, you can look at the tuple square matrices B here, right? Just like E in the upper right-hand corner. And then you could look at that free spectrahedron piece of B, and then that turns out to be what you get by just asking that, and here I have a typo, this should just be, I'm working with just strict inequality. You're just asking that this linear polynomial lambda E evaluated at X should be a contraction. And so here, of course, E doesn't need to be squared. If you go back and look at the previous examples, it's not hard to structure. Here we can rewrite this a bit, but I think it's fairly clear that here, when you're looking at this pre-polydisc, that's a some sort of spectral ball. Here, this is clearly the column ball. It really has this structure, right? We've got the EX here, or lambda EX in the upper right corner. Well, maybe it's better without it. But this twisted ball isn't, right? So that's an example of something that's free spectrahedron, but not a spectral ball. Okay. And then these free spectrahedra, why you care about them is they appear sort of at just the scalar level in engineering and control, but also these at these matrix levels as well, particularly in terms of problems that are governed by a signal flow diagram. Those lead to matrix inequalities, sort of a generalization, nonlinear generalization of linear matrix inequalities. Of course, that they're connected to ordinary spectrahedra, right, at level 1. There are connections to completely positive maps, operator systems. I'll say a little bit more about that. And then when you look at spectrahedral inclusions problems, it's sort of relevant, it's natural. And in fact, I'm going to discuss that in a little bit more detail. It's just an example here in a moment. So maybe I'll just move on to that soon. Okay. So in terms of the inclusion, so again, if we start with a tuple of G tuple of R by R matrices, we can take the span, the unital span of this tuple along with the adjoints as well. If we want, that gives us some sort of operator system. And then a unital map from this script SA, this operator system, into matrices of some size, is said to be positive if it takes positive elements to positive elements. So if S is positive, implies its image under phi is positive. And then phi is said to be completely positive if the following holds. If you take now an M by M matrix whose entries come from this operator system script SA, so we build a block M by M matrix with entries from SA. We ask if that's positive, then it's what we get by taking the entry-wise, we apply the map phi entry-wise, should be positive. So that's this M by M matrix now, I guess, with the entries that are of size E by E, that should be positive for every choice of M, right? If you say for a particular choice of M, that's M positive, completely positive is M positive for every M. And so here, at this point, we could think one of two ways. Either we're handed the A and the phi, and then we just set Bj to be the image of the AJs under phi, Bj star the image of the AJs, AJ stars under phi, or we could think to ourselves, we're given the B's as well, and we define phi in this way. Either way, saying that that you have this inclusion. So this is an inclusion now of I don't want that inclusion. I want, so that's a typo. I want this inclusion. So this inclusion is saying that this map is completely positive. Okay, so that's an alternate way of thinking about it. And then we'll want to look at maybe mutual inclusion, is asking that we get both inclusions, and that's saying both phi and its inverse are completely positive. That's a map with that properties is known as a complete isometry. And so I just maybe a bit of a detour to review. So the matrix cube problem of Nemirovsky. So you start with, again, so I'm looking at the case. Looking at the case where the matrices are real and symmetric, and we're working with real variables as well. So we're given these real symmetric matrices A1 through AS, and we want to check whether maybe the cube of with whose sides have length rho, centered to the origin, whether the cube fits in the corresponding spectrahedron. So that's saying X is in the cube. You want that to imply that this LAX is positive. Okay, or in other words, X in the cube. You want that to imply X is in this spectrahedron. And so here's a nice picture again, thanks to Igor. So this is our convex set from an earlier slide. And then, so they proposed, Nemirovsky, Bental and Nemirovsky proposed the following relaxation. So anyway, so the matrix cube problem itself, this problem of inclusion of the cube into a spectrahedron, it rises to the problems of robust control, various combinatorial problems. The issue with it is it can be typically is NP hard. But if you take the free relaxation, so you replace the inclusion. So you take, so here's the problem. You want to look at this inclusion right here, inclusion of spectrahedra. So that the cube then is just of size with sides of length rho is just scaled the free polydisc, again, the real version of the free polydisc by rho, and asks does it include in the spectrahedra PA. The free relaxation just asks then, well, does some scaled version of the free polydisc include into the spectrahedron piece of A, right? That's tractable. That's a semi-definite program, and that's something you can solve. And so Bental, that's what they determined. Bental and Nemirovsky did. They determined the sort of the cost, the make in that relaxation. So replacing this NP hard problem by this relaxation that's very tractable. There's of course some error involved in it, and that's what they computed. Of course, they didn't interpret it as a is inclusion of free spectrahedra. This sort of an operator theorist take on what they did. And of course, once you do this, then you can imagine many different versions, sort of abstract versions of this this problem. Okay, so anyways, back to these spectrahedral inclusions. So the inclusion PE into PA, again, the spectrahedron determined, free spectrahedron determined by E into free spectrahedron determined by A is equivalent to a map being completely positive. It's some map at matrix level, so that's completely understood. That just says E dilates, or is a compression of some number of copies of the tuple A. So IM tensor A, you could think of that as just a direct sum M times. And then the V, you could of course arrange the V to look like so. Okay, and then writing it this way, then the V's, this decomposition becomes the Krauss, I guess the V's are the Krauss operators or something like that in quantum information theory. So that is just standard theory of completely positive maps. If you want to look at the mutual inclusion, let me introduce some terminology. So we'll say that the tuple A is minimal for a free spectrahedron P. Of course, at PA, it should determine, the tuple A should determine the spectrahedron P. And minimality is if you take any other tuple that gives you the spectrahedron P, then the size of B should be at least as big as the size of A, or the size of A is minimal amongst the sizes. So that's the D here and the E for the B. So that's the minimality, it's just sort of a minimal size condition. And then so it takes a bit deeper is the fact that that any two minimal tuples for a given spectrahedron, free spectrahedron, are unitarily equivalent. So that's B is just unitarily equivalent to A. And of course, the unitary equivalence is entry-wise here. Okay, so that's see now the talk begins. That's sort of a view of the linear theory. What I want to look at is what happens when you move beyond linear. So a place to start is with just free polynomials, also known as non-commutative polynomials. So we had our variables x1 through xg, which were essentially just placeholders up till this point. But now we want to think of them as non-commuting variables, freely non-commuting, no relations amongst them. And then we have the words in those letters X, sort of the natural things. And then if we look at finite C-linear combinations of words, that's often called the free algebra, the algebra of non-commutative or free polynomials. And so here's a couple of simple-minded examples. I guess I emphasized this one to just point out the non-commutative nature, right? X1, X2 is not X2, X1. And then, of course, the whole point is we're going to want to start substituting tuples of matrices X for the variables little x. So capital X for these G tuples of n by n matrices for the variables. And if you just do that, and if I didn't have the slide, you would just automatically do this, right? Wherever you see you want to take x to the power alpha, you just do the canonical thing. You just replace xik with little xik, the variable, with the matrix x, capital Xik. And then, of course, when you have the scalar 5, when you evaluate, you have the identity, appropriate size identity. We'll also want to evaluate matrix polynomials. So here's say a matrix polynomial. And there we'll evaluate using the tensor product You could also, of course, think of it, if you wanted, is your matrix polynomial is a mu by mu matrix whose entries are scalar polynomials, and just evaluate that way if you wished. Doesn't matter, all the same, up to unitary equivalence. Okay, and so here's maybe a warm-up example. So I took E1 to be this matrix here, E2 to be this matrix. Of course, E2 is just E1 squared. We take F to be minus E, and then we get these two linear pencils. And I'm going to consider these two polynomials P and Q. And then something you can just check barehandedly, and if you want a distraction for the remainder of the talk, you can work it out. You can check that LE applied to X is positive if and only if LF applied to PX is positive. In other words, X is in the free spectrahedron determined by E if and only if P of X is in the free spectrahedron determined by F. And that's for P, then you show Q as the inverse of P. So it's telling you that this polynomial P is somehow giving a polynomial equivalence between these two free spectrahedra. Okay, and in this example, well, it's rather simple. You can actually check that P and PF are actually linearly equivalent. I think you just send X1, X2. Don't quote me on this, but I think it's X1, X2 goes to X1 minus X2. Is it still linear equivalence between the two? But there are examples where the spectrahedra are polynomially but not linearly equivalent. So beyond polynomials or rational functions, so here's an example. The kind of expression is an operator theorist, the kind of thing you might end up looking at. So it's got you take some polynomials, you take an inverse of a polynomial, you multiply by stuff, variables, take another inverse. That's an example. So it turns out, I haven't actually said what a free rational function is. I'll do that in a minute, but one with zero in its domain. In other words, it makes sense. You can plug in zero. We didn't ever take the inverse of something and get something that would be undefined at zero. Has a realization, what's known as a realization. So it's an expression of this form. So you've got this inverse of this pencil. This time it's really an analytic pencil. There are no adjoints involved. And so you have this E of same size, capital E of size E, and then B and C are vectors of size E. You'll get something that's scalar valued out of it. And then, so this, in fact, for this talk, you could really think of that as what's meant by a free polynomial, or excuse me, a free rational function. And then you can evaluate that thing in the obvious way, right? You just plug in X, and then of course it makes sense as long as this inverse actually exists. So as long as that inverse exists, this rational function is defined. So that's sort of the canonical domain of this rational function. And maybe I won't say too much of this. I mean, it's a bit more, another way of thinking of rational functions is equivalence classes of rational expressions. And if you start with this rational expression, you can do some algebra and get this rational expression. And then the key thing is you'd say two rational expressions are equivalent if they agree where they're both defined. And what sort of the amusing thing about this example is the first one is defined is at 0, 0, but the second one isn't. Likewise, the second one's defined at 1, 1, but the first one isn't. But sort of if you write down a realization for this rational function, you get this expression, which of course will be defined at both 0, 0, and 1, 1. It just depends on how you want to compute this inverse right here. Okay. And then even more general are free functions. So I'm just for free function, I'm just going to worry about things being defined for this talk. We're really focusing on free spectrahedra. You could of course do this quite a lot more generally, but it's just a sequence of functions, right? At every level, you have a function fn, and then these functions need to fit together in a coherent way. And so what you want is, if you apply the f to a direct sum, that should be the direct sum of the f applied to the factors, the x and the y. And keep in mind here, x and y are both themselves G tuples of matrices of size n and m respectively. So you want to respect direct sums. You also want to respect unitary conjugation. So you want f applied to, you take the unitarily conjugate the tuple x and apply f. You want to be the same as evaluating f at x, and then taking the unitary similarity. And then I'm going to assume that the f's are analytic throughout the talk, as just saying each fn is analytic. We'll quit writing the bracket n, keeping track of the size. And then the key thing is, if you want to just think about rational functions or even just free polynomials, that's fine. Those are examples. And then under some mild assumptions, and which are always going to be enforced for me, our analytic function regular at 0 is going to have a power series expansion. So you could think in terms of power series if you wanted as well. Okay, and so I want to look at mappings from one free spectrahedron to another. So that's going to be a G tuple superscript F superscript 1 to F superscript G, where these FJs are themselves free functions. So for me, analytic included. And of course, you want to take a tuple X in the spectrahedron PA, the domain of F. Its image should lie in the spectrahedron PB. That's what we want to look at. And then you could think of, particularly if you added the condition, it's not really essential, but some normalization. Then mapping one domain into another is a sort of a nonlinear inclusion. And you could of course write it out sort of concretely in terms of the monoclinear pencils, right? You want LAX positive should imply LB of F of X positive, or in other words, L composed with F is positive, where L sub A is positive. This should be LB. Let me fix that. There we go. And then mutual inclusion would be asking that F's bijective. Okay, and if that happens, then it'll turn out that the inverse map is you'll have an inverse at every level then, but in fact, it'll be a free mapping. So we'll refer to it as being bianalytic. We'll say that PA and PB are bianalytically equivalent. Okay, and you could think of that then as a nonlinear analog of a complete isometry. Okay. And so then there's a question of both sort of characterizing, being certifying, maybe given an algebraic certificate for inclusion and mutual inclusion. So for the inclusion, here's a version. So we're allowing G to be matrix valued analytic function defined on our spectrahedron. And then I have G of 0, take G of 0 to be 0. And then we could look at the condition that LAX positive, in other words, X is in PA, implies that I plus GX star are positive. Okay, so that's if we assume that, then, or maybe say that can be certified by the following representation. So if you here, H is a Hilbert space, and so you can think of this, oops, you can think of this bit right here is just copies, some number of copies, right? Direct sum of A with itself some number of times. And then we multiply by W and W star. So clearly if LAX is positive, then that's positive and the whole right-hand side is positive. So if you have this representation, then LAX positive implies that I plus G star is positive. And then the theorem is that the converse holds. Okay. And I have to say, the statements may be slightly more technical, but I took a little bit of liberty on that. And then our application is this setup again, back just this previous slide, this condition right here, where I'm taking f of 0 to be 0, f prime of 0 to be the identity, and then the g just becomes, in that case, I guess that's minus g, right? Like so. So that's going to be the setting, and then I'll come back to that after a bit. Okay. And so then the mutual, so this, in any case, this handles the inclusion problem, and it actually use this result, we'll actually use it for the mutual inclusion. I guess that's not a shock. But anyway, so that mutual inclusion problem would be to classify triples A, F, and B, where A and F, excuse me, the spectrahedra determined by A and B are bianalytically equivalent, and F is a bianalytic map between them. Okay, and then so some motivations, further motivations might be, it's a sort of a free analog of some of the sort of rigidity results you see in several complex variables. It's also would be represent the non-uniqueness if you're trying to map the solution set of a matrix inequality that might arise in some sort of application to the solution set of a linear matrix inequality where you now have convexity. Okay, so there's going to be potentially a certain amount of non-uniqueness, and then that could be measured in terms of maps between two free spectrahedra. Okay, and then the conjecture and borne out for the most part is that there aren't very many of these triples, and there are even fewer of the maps F. And then they're what we call, what maybe Bill calls convexitonic. And so let me tell you what that means. So convexitonic tuple chi, so that's a G tuple of G by G matrices, and it's convexitonic if this relation holds. So maybe I'll come back to that in a second. Anyway, so then it's not hard to see if you iterate that for any word alpha, you end up with this sort of expression right here. And then the thing to observe you could observe is that if you have a tuple of matrices that spans an algebra, so matrices, G tuple of square matrices that spans an algebra, then these maybe you call the structure constants, these coefficients here form a convexitonic tuple. And so then if you have a convexitonic tuple, what happens is well, that tuple spans an algebra, and that tuple's like its own structure constants. Okay, so that's what the notion of a convexitonic tuple. And then a convexitonic map, where you build it from a convexitonic tuple by this sort of linear fractional expression right here. So here I wrote it out, expanded it out. So X, I'm thinking of the X now is a row vector. And then of course, this guy is going to be a G by G matrix polynomial, or rational function, excuse me, in these variables X. And so that's what we'll refer to as a convexitonic map, anything of that form. And then you can check that that if you replace the tuple chi by minus chi, that'll again be convexitonic, and you get the inverse that way. You get the inverse of f sub chi. This convexitonic map is just gotten by replacing chi by minus chi. And then again, it has this normalization. It sends 0 to 0. Its derivative at 0 is the identity. That's just sort of automatic. And then again, sort of what you would expect is that f is a polynomial if and only if chi is nilpotent. And so you immediately get some bounds of if for a G tuple chi, then a polynomial to be convexitonic, it can have degree at most G, for instance. There are certain that already imposes quite a lot of restrictions. Okay. So here's an example, sort of slightly rigged to go along with the earlier example we looked at. So I'm going to take R2 to be R1 and R2 to be these matrices here, and then you can check that R spans an algebra. R1 squared is R2, and then the whole thing's nilpotent, right? You multiply again by R1, you get 0. You multiply anything by R2, you get 0. So that's spans an algebra, and then you can check that it's, so then you want to compute the corresponding convexitonic tuple. Well, here it is. It's rather simple. And then the corresponding convexitonic map, again, you just plug things in, and you end up with this polynomial P from an earlier slide. Okay. Okay, and so here's sort of excuse me, a direction. So we start out with the convexitonic tuple chi. Then we can pick any tuple R that spans, I'm going to call it spanning a chi algebra. In other words, an algebra whose structure constants is chi, right? Take any old n by n unitary matrix C, but we assume that C minus I is invertible. And then take choose A this way, and B to be C times A. So A is C minus I inverse times R, B is just C times A. And then the corresponding convexitonic map is a bianalytic map between these two free spectrahedra. Okay, so that's so what it tells you is that once you have a convexitonic tuple, well, it determines a convexitonic map. But then going with that map, there's a whole family of pairs A and B. So the triple ABF satisfies the condition that A and B are bianalytic via F. Okay, and so if we look at the R from the previous slide, that was R1, R2 was minus 2 times 0, 0, 1. So if we start with this R, take C to be minus the identity, and then pick E to be the C minus I inverse times R, so that's minus 1/2 R. That was just the E we had from before. E1, that is, and E2, just this guy. Then F is minus E, it's C times E, that's minus E. And we're right back to this example we had earlier. And then we have, that goes with this convexitonic tuple chi1, chi2. And then again, we have our corresponding convexitonic map we computed before. And so it's telling you this map P is a bianalytic map between these two spectrahedra, P and PF. So that returns us back to our warm-up example from earlier in the talk. Okay, so if you look, here's a case, if you're looking for a bianalytic map from a spectral ball, BE to a spectrahedron PA. So those are convexitonic. So those are convexitonic, and in particular that are automatically birational. And there's a bit more that you can say. If you assume that E and A are minimal, so we already talked about minimality for A, for a tuple that defines a free spectrahedron. There's also a notion for minimality for a tuple E that defines a spectral ball. But if we're assuming that those are minimal, then we make a affine linear change of variables so that we start with our map F. We're not assuming F sends 0 to 0 or that F prime of 0 is the identity. So we make that corresponding affine linear change of variables so that phi satisfies those two conditions. Then we get a new tuple F, and then the tuple F is related to the tuple E in this way, right? So here B and U are unitary matrices. So the tuple F just looks like this, what you would tuple that would define a spectral ball up to, well, unitary U on one side and unitary B on the other. And then it's not hard to, so these statements are if and only if, it's not hard to see that the converse is true as well. Yeah, and then maybe I'll say just a little bit about an ingredient, I think an interesting ingredient in the proof is, so let me introduce some notation. So QE will be just I minus lambda E star lambda E. And then the spectral ball BE can also be realized as just the set of those tuples of matrices X where QX is positive definite. And again, we're making some minimality assumption that the tuple E is minimal for the spectral ball BE. And then we have some matrix polynomial. The only constraint is it's got to be the right size for the formulas to make sense. And then what we're assuming this condition here is really going to be the condition that B vanishes on the boundary of BE. And so by boundary of BE, what I mean is tuples Y gamma. So Y is a matrix, gamma is a vector, for which QE Y is non-negative, positive semi-definite. That's just saying Y is in the closure of the spectral ball. And then you want to say it's actually in the boundary. That means, well, this guy should have a kernel. And it's saying this vector gamma is actually in the kernel. Okay, so you take this pair Y gamma, Y is in the boundary, gamma certifies it's in the boundary. And then what should happen is that BY applied to gamma should be 0 as well. So that would be one way of saying that B vanishes on the boundary of the spectral ball BE. If that happens, then B is 0. So this is some sort of Null-Stolensatz, and I think it's certainly natural from the point of view you sort of think, an analytic function somehow vanishes on the boundary of a ball, that it should be 0. Okay.
Scott, you have 3 minutes for this.
Pardon?
I was saying you have 3 more minutes more.
Yeah. Yeah. Okay. Thanks, Daniel. Yeah, I think in fact maybe I'm. Yeah. 3 minutes. Okay. Maybe that puts me. I'm already 8 over or something. The 40 minutes. So okay. Let me just. Yeah. This is a lot. So I won't maybe say a whole huge amount about it. But in the case of, if you're mapping spectral balls to spectral balls, so then they're completely characterized, right? If it's analytic from one spectral ball to another, then it's automatically convexitonic. But you can actually say quite a lot more. You can actually give more or less explicit conditions that tell you when that happens, just based on the data. You have the tuple E, you got the tuple C. There's some existence of unitary matrices V and W that tell you, right, would certify when this happens. And unfortunately, I didn't time things very well. I wanted to mention the result of my a recent PhD student. She takes this corollary and determines those spectral balls for which the automorphism group at level 1 is transitive, and then those are correspond to what people refer to as ternary rings of operators. So anyways, I'll stop here.
Thank you. Are there questions in the audience or online? Questions, remarks? I cannot see the people online. You have a problem with technology, but other questions, no?
Yeah.
Well, yes.
I'm not seeing anything in the chat, Daniel.
Sorry.
I'm not seeing questions in the chat.
Okay, so because usually I understand the system, but here I don't know, there is something a bit different. Okay, so if there are no questions, so let us thank the speaker again. Thank you.